Hi everyone, this is Reem Goody from Computer Science Department in the University of Texas at Austin. And today we're going to present unsupervised fine-tuning data selection for ASR using self-supervised speech models. This work has been conducted by myself and Professor David Harbath, who is the head of the SALT lab in the University of Texas at Austin. So the motivation behind this work is that self-supervised learning has shown great promise when using large amounts of pre-training data to pre-train the speech model, and then selecting some subset to transcribe and fine-tune the model for a certain downstream task, which is ASR in our case. When we are confronted with low-resource domains or languages, the audio data that is available for annotation is usually very small, and we have to be wise about our selection of subset to annotate and use for fine-tuning. Whenever we're using small subsets for fine-tuning, this can lead to lower cost and time. But in the same time, it can lead to higher variance in performance in terms of WER, depending on how we choose the fine-tuning subset. So how can we be wise in our selection of data that we transcribe and use for fine-tuning the model for ASR task? And whether we can find unsupervised techniques for data selection so that we do not rely on having access to transcription or metadata. So formally stated, our problem of interest is that we have a pool of unlabeled data, and then we need to select some small subset of data from this pool in an unsupervised way, and use that subset to fine-tune a self-supervised speech model like HuBERT for the ASR task. We propose two novel techniques in our work, which are a Perplexity-based data selection technique. This one leverages HuBERT's k-means clustered units, and another technique that leverages the pre-training loss of the HuBERT model. In addition to this, we investigate some other criteria for data selection to probe the impact of different variables like speaker diversity, gender bias, and topic diversity on the downstream performance. We summarize our contribution as follows: devising two novel techniques for unsupervised data selection, the PBPE and the pre-training loss-based one, and comparing these to pure random selection, investigating the impact of speaker diversity, gender bias, and topic diversity on the downstream ASR performance, and showing that these can result in achieving better performance in terms of WER. We also conduct a thorough analysis of the correlation between the inherent characteristics of the fine-tuning subsets and the WER on the test sets in our scenarios. Our experimental setup is as follows. We have the HuBERT model as the model or the pre-trained model that we use, a data selection pool, which is the full 960 hours of libre speech, and then we select a limited amount of data for transcribing and fine-tuning the model. We limit that to 10 hours in our low-resource setup. We evaluate the performance on the ASR task using the WER, and our evaluation data sets are libre speech as an in-domain data set and common voice or TEDLium as out-of-domain data sets. So our data selection criteria probe first, we investigate some criteria that rely on the access of metadata just to probe the impact of these criteria on the downstream performance, like the gender, bias, the utterance length, the speakers, or the diversity of the speakers, the book diversity, as well as our two novel criteria, the pre-training one and the perplexity one. Describing the Perplexity-based data selection criterion, we know that HuBERT uses k-means clustered units to generate labels for untranscribed speech to use during pre-training. We hypothesize that these labels are correlated to the tokens in the actual text transcript. So we come up with the idea of building a language model on top of these tokens, and then scoring the utterances using this LM, and using the scores that we generate to select the data. So we start with the audio data. We use k-means clustered units discovery to find the k-means units. We compress them down using run length encoding because multiple frames would be associated with the same label. We build a BPE model on top of these units, and then on top of the BPE tokens, we build an LSTM model, a one-layer LSTM model, and use that for the perplexity scoring of the BPE tokenized utterances. And then we sort the utterances in terms of the perplexity and select from the top 15% or the bottom 15% and compare both criteria. For the pre-training loss-based data selection, we use HuBERT pre-training loss to compute the score for each utterance. The HuBERT pre-training loss is a weighted average of the masked loss and the unmasked loss. So we start by computing the scores of the utterances as the average masked pre-training loss. And then we notice that this exhibits some randomness by default because the masks are randomly chosen. So we turn off the mask and use the average unmasked loss as our score for the utterances. These are the results that we obtained. First, we observe that the WER is 8.93% for the Perplexity-based data selection when selecting from the top 15% of the utterances with the highest Perplexity score versus 9.36% when selecting from the utterances with the lowest Perplexity score. On test clean, the mean WER for tail is 4.25% compared to 4.42% for head, and we observe that the tail is consistently better than the head. For the average masked pre-training loss, fine-tuning with the utterances with the smallest loss leads to 9% WAR on average on test other and 4.28% on test clean. Using the largest lost utterances leads to a mean WAR of 9.36% on test other and 4.46% on test clean. For average unmasked pre-training loss, the mean WAR in test clean is 4.23% when sampling from the 15% of the utterances with the largest loss, and degrades to 4.41% when sampling from the 15% with the smallest loss. For test other, the mean WAR is almost the same for both head and tail, which is 9.1%. The best results from our proposed criteria are almost on par with pure random selection, which scores a mean WAR of 9% on test other and 4.24% on test clean. We hypothesize that this is the case because pure random selection is done on library speech, which is inherently diverse in terms of number of speakers, tokens, as well as topics. Increasing the number of speakers by default leads to a significant boost in WER on both test clean and test other. We also observe that the WER does not vary much regardless of whether the 24 speakers were of the same gender or whether they are selected randomly. We also observe that the mean WER significantly improves when increasing the number of audiobooks from 16 to 64 in our case, on both test clean and test other. We then did some thorough analysis on the correlation between the WER and the inherent characteristics of the fine-tuning subset. We observed that a strong negative correlation exists between the WER and the number of the unique vocabulary words, as we can see here. This correlation is stronger than the correlation between the WER and the total number of vocabulary words in the fine-tuning subsets. We also observe an interesting correlation between the average masked loss or the average unmasked loss, as well as the number of utterances selected from train other and train clean. This could imply some biases that occurred depending on how the utterances were fed to the model during the pre-training with the library speech data. One other interesting observation is the strong positive correlation between the number of unique vocabulary words and the perplexity computed over the BPE clustered units. We also observe that increasing the number of unique vocabulary words results in a lower WER on the fine-tuning subsets as observed by the trend in this figure. This is an interesting result because we can use the PBPE to drive more unique tokens in our fine-tuning subsets and hence obtain a lower WER in our unsupervised selection setup. Since we observe that increasing the number of unique vocabulary words as well as speaker and book diversity can result in a lower WER, we combine some of these criteria together. And we observe that when selecting utterances from either all the speakers or almost all the books in the top 15% high scoring utterances in terms of perplexity over BPE clustered units, we're able to beat pure random selection on test other, test clean, and TEDLium. Also compared to fine-tuning the HuBERT-based model with Library Light 10-hour, which has some balance in terms of speakers as well as the number of utterances from train clean and train other, we obtain better scores on all the test sets in our experimentation setup, as we can see here. So our conclusion is that our proposed criteria PBPE maximizes the number of unique vocabulary words in the fine-tuning subset without having access to the transcripts. Speaker and topic diversity are very important and lead to a better WER. When combined with speaker diversity, PPPE leads to better WER and beats pure random selection. Data selection based on pre-training loss can inherit some biases from the pre-training stage depending on how the examples were fed to the pre-trained model, and pure random selection can be hard to beat as it guarantees topic, vocabulary, and speaker diversity as long as the data selection pool is inherently diverse, and this may not be the case if the pool does not have enough diversity. With this, we conclude our presentation, and we'd like to thank you for listening.